The broadcast is now starting. All attendees are in listen-only mode.
Welcome, everyone, for attending our first session of the HyperMesh HyperView training. And this is our first session of our fall webinar series. We're really happy to have everybody that could make it. And I know one of the questions people always ask is, will this recording be made available? And we will make the recording available 2 weeks after the class is done. And then so you'll be able to stream it that way. So my name's Darius Fontanelli, and I'll be the moderator, and I also will be taking any questions I can. And if I can answer them, if not, I will then try to pause our trainer, which is Garrett. Garrett has been with Altair for about 5 years now, and he is actually in charge of our training for the North America operations. He does a lot of training classes for HyperMesh HyperView for a lot of large companies, and is a fantastic trainer. So I think you'll enjoy today's session. He'll be able to handle almost any question you have. He's familiar with a lot of our solution techniques and so forth. So again, feel free to ask questions that are relevant, and he'll do his best to answer them. We'll also, if we have time at the end, and take questions there too. As you can see, everybody's muted. That's just so we have a good audio recording. And there were some questions about the link to download the files for the training. Go to the chat window and check that out there and see if that works. If there are still issues with it, we'll try to get that resolved so you can at least have them before tomorrow's session. Because I know right now, since we're in the middle of everything, if the link isn't working, we might have to make a new link and provide that for tomorrow. And again, yeah, the recording will be available 2 weeks after the session is done. I suspect most of you already have access to our tools or a sponsor team. Many schools have access to our tools in their labs, and then many teams also have access to it. But if you're not a sponsor team, our sponsorship is extremely easy to get. Pretty much you just fill out a form. If you go to our Altair HyperWorks.com website, you can go to our Academia tab, and then you can go into the students, and you'll see option for teams. And you go in there, there's a very simple form to fill out, and then after that, we will send you another agreement to sign that also states what machines you want it on and so forth. So you can get access to multiple copies at the same time. So you're not limited to one copy. If you need 20, you can get 20 copies. Typically, most teams only need 3 or 4, but if you have a lot of people want to use the tools, that's fine too. The software that you get as a sponsored team is our full version. So you have the ability to make as large model as you want. There's no issues with proximity to the license server. You can be using it anywhere in your region, and you can also send technical support questions to our support line, hwsupport@altair.com, and get some help. Now, of course, many teams do work after normal business hours, so I would suggest then to go to our form that's on our academic sites, and first check that out too. It has a lot of questions answered there, and there's people actively on that, so you can send a question there, and if they don't answer it, then send it to us, and we'll get to you shortly thereafter the following business day. I don't want to take any additional time from today's session. We have a lot of material to cover, and Garrett's probably getting really antsy to get up and show you guys everything. So again, I appreciate everybody being here, and if you do have any questions, please put it in the question window, and I'll see if I can answer them. If not, I'll get Garrett to help. Hey, Garrett, I'm now going to give you permission to present.
All right, let's first make sure I get the correct screen up here, folks. If you just bear with me for one moment here. There we go. Should have the HyperMesh session up. Yep, that is correct. So thank you everyone for finding some time this afternoon to be here. As Darius mentioned, my name is Garrett Ackner. I wear a few hats within Altair here. As Darius said, I currently working with our training schedule and our training team here. So really why that matters for you guys is I've probably taught this course dozens of times. I've lost count, frankly, at this point, with both students such as yourselves, folks that have been doing this longer than I have been alive, and kind of everywhere else in between there. So certainly happy to kind of pull through a few different past classes and experiences that I've had to help you guys out kind of learning the tool throughout the next couple days together here. Now, one of the things I like to do while I'm going through this here, let's see if I can make sure I'm pulling this over correctly here. I'm going to be a big fan of little note sheets while we're going through this. So to help kind of balance the different materials we'll have, and we're going to use a combination of lecture slides, demo models, as well as a few of these kind of hand-typed notes. I'm going to do my best to both save and share these with you guys at the end of the week here. So anything we kind of talk about or write down on one of these little text files here together, this is a sample note sheet here. I'll make sure I'm kind of sharing and making these available to you guys. Now, a few things. I'm going to do my best to keep an eye on the chat window and the questions that are coming in along with Darius, but if I don't answer something right away, don't be offended. It might be coming up in the near future there. So hopefully our questions are kind of leading to our next topics there. So just wanted to address that here. And before we go too far here, I know a lot of you are probably still downloading the materials. It's okay if you don't have them immediately accessible and those are still being pulled down. We're not going to hold it against you. But what I would like to talk about, it's not my Outlook email. Let's close that here. I do want to talk just a little bit about the files you guys have access to here. So what I'm going to do is pull up my little file explorer and do my best just to talk a little bit about the folders we have in here. So I apologize, it's a little small to see on the screen sharing there, but once you do get those that zip folder pulled down on your machine and you're able to poke your head through it, there's a couple things I want to talk to you guys that you're going to have access to. So included in your little student materials folders, you're going to have a student PDF slide folder. You're going to have an additional folder labeled student exercise and a third one in there labeled student manual. We're going to be sharing our student PDF slides together. We're going to be going through a handful of these PDFs throughout the today and tomorrow, and our final session on Thursday. So we have a couple different PDFs or lecture slides, if you will. We're going to steal some notes from. In our student exercise folder, again, these are broken down by the same chapters as a PDF slide. These have sample models that we're going to steal for a few demonstrations together and for you guys to try some things out either while I'm going through it or if you'd rather wait till after class, either is fine with me. And probably most important though, don't want to forget this, in your student manual folder, if we take a peek in here, you're going to find some more PDF files. And again, they're going to be organized by chapters. But if we pull one of these up, such as our Chapter 2 Geometry slideshow, what these student manual documents are going to be is a step-by-step guide in how to complete all of the exercise given to us. So we only have, I believe, a total of 6 hours, give or take, for the week together here. I wish I could say you guys are going to leave here after 5 hours and 55 minutes as the ultimate experts of HyperMesh. Hope I'm wrong. That's typically not the case, but I'm hoping that today we can, or over the next couple of days here together, we're going to get people very familiar with the basics, know how to ask the right questions, know how to help ourselves out when we run into a few questions here outside of the basics. But more importantly, we're going to leave you guys with some take-home materials for you to try on your own or review through on your own time if you're looking to get a little bit more involved with this and have the time to maybe go beyond just the beginner level and basics of meshing and model building using HyperMesh software there. Now, with all that said, I'm going to dive in here, and if I bring back up my HyperMesh session, I have a lot of things open, pardon me. Don't want to close webinar. There we go. Now, this model that I have pulled up here, just for reference, again, is in your student exercise folder there. This is actually exercise in Chapter 1. There's a Chapter 1 exercise model 01A-GUI, graphic user interface. And this is the model I'm just going through for reference. Now, once you're able to get everything installed, and hopefully people have the packages installed on your machine, for those of us using Windows, you can always just search on your bottom left little Windows toolbar to search for HyperMesh software. So for me, I know that if I just type HyperMesh in, it's going to pull my own list of all the different builds I've acquired over the last few months here for different customer purposes. But just wanted to let you guys know that I'm using the latest HyperMesh 2020 software. It's okay if you have access to 19 or 2020 here. Frankly, there hasn't been too many breaking developments or anything between the releases for this particular product, but just for disclosure, wanted to kind of let people know which product I'm using. Now, once you get HyperMesh launched, how do we actually bring in my crane model? What the heck did I just do with it there? So HyperMesh, and I'll be the first to admit, is a busy interface. There's a couple things going on here. My goal for today is to have us be familiar with the interface and know how to navigate around the product and navigate within our own models that we're working with. In a little bit here, once we get the ball rolling, we're going to take a look at some basic geometry editing tools, working with solids, working with different surfaces to split those up. And we're going to end today with some basics of surface meshing. Now, it's okay if all those are new terminology. We're going to kind of start slow here. And moving into tomorrow, though, we're going to spend quite a bit of time using the product's namesake with a lot of the meshing tools available to us and really go from there. So just to reiterate one last time here. Agenda for today here, Monday, I want to make sure we kind of weave here with the following skills. We should be familiar with the user interface, basics of managing our geometry, whether it's simplifying things, making some basic edits, making some basic splits or cuts, and intro to 2D meshing. And again, we'll cover what these terms are and why we need to do those things once the time's kind of ready for those. Now, absolute most basic thing of HyperMesh, step one here. So now that we've kind of found in our Windows machine where we can launch those, again, I like to do the search. And certainly within your different applications there should be a little Altair folder. So I know for me, I have an Altair 2019 folder, as well as an Altair 2020 folder for my unique packages. I believe for the student edition, that should be saved the same way. And this, under one of those lists, you'll find your HyperMesh product there. Now, once it's open, typically what I would start with is getting familiar with our pull-down menus here. And there's some very, expected things here, hopefully things we've seen before. I'm going to notice if I go to my file pull-down menu from the main toolbar at the top, I still have some basic operations here. My file new, my file open model, save or save as, and import and export options are all available within this pull-down menu. So really plenty of different ways to save things or bring things in or kick things out of the software. Likewise, there is a basic edit and a view menu as well. So our first kind of mini lesson is we're going to go to our view pull down menu. For anyone here who's got HyperMesh launched already, you're welcome to follow along with me. For those of you that would rather just watch and try later, that's all right with me too. But what I would recommend is coming into this little view pull down menu at the top left of my software. And I'm going to make sure for now I have the model browser checked on. We're going to want to make sure we have the model browser turned on. And we're going to want to also make sure we have the utility menu and the entity state browser turned on. Just a few things there that we're going to want to make sure we all have access to while we're going through some things together over the course of the week. Now, how do I bring something into the HyperMesh? My buddy or my design teammate or my professor sends me a model. He sent me, model1.hm. I have no idea what to do with it. I have no idea how to bring that into the product. At a glance, we can always do file open to bring in an existing HyperMesh model. So I'm going to do that file open operation. I'm going to come into my HyperMesh training, the little files that I have here. I'll go into my student exercise folder and I can point right to that chapter 1 basics and I can load up a .hm model. So if there's one thing we learned today, we're all going to be experts at knowing that the .hm files is the default extension for a HyperMesh model file. Nothing too fancy there. .hm files, we can load those into HyperMesh with file, open, bring those in. So now that I got that in here, we were able to see the assembly. We got this little kind of like a construction claw or something here. I'm sure we've seen these in some dirt pits at some point in our lives. Now, there's a couple things going on though. We see there's things that almost have these checkered lines on them broken up into different shapes here. So I can see the mesh of this particular red claw body where we have all of those different individual mesh lines just breaking up the different elements or the individual shapes that's grown up with. We'll kind of talk about those in a moment. We have some of these more smooth cylindrical bodies. We'll talk about what's going on with the actual shafts of that kind of connection rod built into there. And more than that, though, if we kind of come over to my model browser on the left side of the screen here, let me bring up a little spotlight tool to help out with this. If I come over to the left side of my screen here, we're going to notice right away towards the top left here, I'm turned to this page of sorts called the model browser. And from that model browser, this is going to be my list of anything and everything added into my HyperMesh model. So for this existing crane model, I'm able to come into my model browser and see that we have a couple of assemblies defined. We have something called a beam section collector. Coming down a bit, I have 25 components. I have load collectors, which are organized into load steps. And we even have things like material and property definitions built into this model here. Now, as you'd expect, I can take my mouse and with a left click, I can open up each of these different kind of folders within the model browser. So as an example of that, I can open up my component tree, come into here, and now I can review individually the 25 components that make up this assembly. So we're not going to go through these one by one, but we can come in here and see that I have something called a cylinder's geometry, a pin 2 geometry, the shovel itself, and they have a couple different things associated with them. And that's what I want to talk about first here, is what's in our component browser.
Garrett, so can I interrupt you for 1 second, please?
Go ahead.
Just for those newer to HyperWorks, we're talking about HyperMesh HyperView, and in this student edition, the tool that you launch is called HyperWorks Desktop. So you want to launch that, and that will get you the interface Garrett has here too. In the full version, if you have that because you're a sponsored team or you're have access to school, it's HyperWorks Desktop. So student edition, this is one thing where it's different than the full version, Garrett. So they'll have to launch that. I think you also will probably have HyperWorks on the desktop on the full version. But what again the difference is HyperWorks Desktop has all the other clients, HyperView, MotionView, HyperGraph, all in there at once.
No, thanks for clarifying that, Darius. Now, one thing I can add to that, everyone, is if you're a little confused on what the heck's HyperMesh, what's desktop, sure, Darius just let me know that this has all these other applications in it. For me, it's always just comes down to rectangle square. Everything in HyperMesh is certainly included in desktop. Desktop has a few bells and whistles that are going to be excluded from this standalone HyperMesh application, which I'm currently using. Now, for our purposes, that won't make any difference what we're doing today and tomorrow. On Thursday, once we start getting into HyperView and post-processing, we'll kind of revisit the distinction between those packages. But for now, don't worry too much about that. I won't tell on you if I find out you're using HyperMesh for desktop for today, if you have access to both. But there is a distinction, and if you're ever confused, we're certainly happy to clear that up. But we'll get into a little bit more specific with why that's the case on Thursday there. But I'm glad Darius gave us a chance to kind of address that now.
And also, will you show how to import other solver models when you're going through the interface?
Yep, we're getting there.
Okay, that's what I thought. Thank you.
So if we take a closer dive into our model browser together here for a moment, if I come back, we got the component browser. There's a couple things here. First off, we have a couple different flags. I refer to them as flags. If you got a better term for it, let me know. but we have two flags to the left of each component name. One of them is just a solid blue, kind of nice and wavy flag. It's got the sun shining in it. The other, just to its immediate right, is more of a checkered flag broken into 4 quadrants. It's a little darker, looks a little bit more, frankly, it looks meaner, if you ask me, if we had to assign it a personality. We're not going to get too into that, though. But we're going to come back to those two flags in a moment. Just want to make sure we knew where we could find those. And then, much more simply, though, each component comes with an ID to reference it by, as well as a color you can assign to it. So the ID is more of an organizational tool for you as users. So you'll see here, if I come up to the top of my model browser and click the header, either name or ID, I can actually sort my model browser by either, alphabetical order. I can do it numerically based on those ID flags. So not only will HyperMesh automatically assign a default ID to your components as they're made, but a simple left click of that ID, you can come in here, reassign it a new number, keep things nice and organized for yourself there. And likewise, you could do the same thing with the color palettes as well. So for a moment here, I'm just going to isolate my digger claw on the component. Now, maybe for whatever reason, I don't like this gold color here. This yellow that we have up on the screen. Turns out I hate the color yellow. If there's yellow in my model, I'm going to lose it. So we don't want me to blow a gasket this afternoon. So I'm going to come in here, and just like I did with the IDs, I can left click the little swatch of color. In this case, it's that little gold square. I can left click to open up many other color options here, and I can simply reapply it. Maybe in this instance, we're going to go with a purple color here. I didn't want to update for very specific reasons there. Oh, that's fine. There we go. Now it wants to change colors. I was about to lose it there. We're good now. But just want to show that little things with the components, you control the ID numbers assigned to them, and we can also control the, what's the word I'm looking for? The colors for them as well. Now, what I want to talk about here for a moment, though, as Darius was starting to get us into, is what's going on with those flags that I mentioned next to each component name. So they have an ID. Sounds great, never going to change it. We have colors. I'm going to make everything my university's color scheme. But what the heck's going on with these two different flag settings? Well, this is really getting into the idea of why we need finite analysis in the first place. So what I'm going to do for a moment here is just turn everything off my model for a second and start with just that shovel component again. And I'm actually going to bring it back to that yellowish color to make it a little easier to see here. Now, typically in finite element analysis, a very generic workflow would go to design your part in a CATIA or a SolidWorks or some more traditional CAD package, something that's got a lot of drawing and surface tools to get us not just sketches, but the full 3D model that we can spin. And that's what we're going to typically refer to in the FE world. And at least for the sake of my class, we're going to refer to what's coming out of a SolidWorks or a similar package as just the geometry. That's the geometry file that we're working with, whether it's a CAT part file, a solid part file, whatever else you can get out of these tools. And if I zoom out for a moment, what I have on the screen is just the CAD file that's been imported into HyperMesh. Now, what we're responsible for on the simulation side of things typically, and where finite element analysis is going to be introduced to, is we are going to discretize these geometries into a form of a different type of geometry that we're going to refer to as a mesh, that not only can a computer read and solve math problems on that's been defined in the software, but and that's really where we're going to kind of be getting at with this thing. Is this idea that we're going to take this geometry file and we're going to need to discretize it. We'll talk about why in a moment. So coming back to our flags, though, we do have a single flag that represents the geometry or the original CAD for that part. So right now I only have those left flags turned on in the model browser. I apologize for them being a little small, but the video sharing and I don't get along. You can try to change the application size. And then the other half of it, though, is that mesh that we're going to generate. So you can almost think of the left flag or the geometry flag as the starting input that my designer gave me. And now what I'm going to be building are the checkered flags or the meshes themselves here. And now if I zoom into these, Now we're not just seeing a perfectly smooth surface across my digger claw. I'm starting to see these various squares and triangles that were now created on the surface. And this is actually what we're using to represent a part now. It's going to be these squares and triangles, or tomorrow we're going to see we can use cubes and wedges and pyramids as well to represent parts. And that's what we refer to as a mesh. So those individual shapes, those tiny bits of the surface or tiny bits of the part, those are the mesh that we generate. That's why the company charges the big bucks to have access to the software, because that's the real star of the show. And that's kind of what I want to talk into here for a few minutes by putting the software away for a moment here. Now, there's a few questions I'm going to come and get to in a moment here. I see those coming in. I want to do a quick little background on the theory lesson here, make sure we all got our feet on the ground and we're on the same page moving forward. And then I'm going to come back and kind of address those with Darius here in a moment.
Yeah. Garrett, all the main questions have been taken care of, except someone's having trouble from maybe one of the files. But
perfect. Thank you, Darius. So what I want to talk to us about today here is what's going on with finite element analysis. What actually is finite element analysis, and why do we need HyperMesh for it, and what's the benefit of this? So I apologize for those of you that have been working with your university. I'm sure many professors have walked some of you or maybe all of you through this. My goal is to not replace that university level of teaching of these. I want to make sure we got a quick 5-minute lesson that can get us all on the same page together here for the week. Now, some of you back in your schooling days might remember some really easy formulas for things like those moments of inertia, as an example. And I'm going to pull these up here, just to remind us of our favorite physics 1 and 2 days for those of us done with those here. This is a good slide for me to talk about that very quickly. So nothing too crazy here. Just did a quick Google search here, and I'm sure some of us remember or are actively in classes that are dealing with a lot of these formulas. And for those of us that aren't as familiar, it's a very nice tool. Some people much smarter than me figured out that for objects with a basic shape, think perfect cylinder, a perfect sphere, an ideal thin rod that's perfectly uniform, it's very easy to describe the mass properties or other geometric properties of that shape because it's such an ideal perfect square, perfect cylinder, whatever it may be. But you'll notice here that we don't have a formula for the 2017 Ford Fusion upper control arm. How the heck do I calculate the moment of inertias of those? Or something else that's a little bit more complicated. Now, I can already hear you guys in my head. There's someone much smarter than me in this room already saying, well, Garrett, you know better than that. You could probably integrate. And there's many other numerical methods we could do to solve those. And you're 100% correct. That absolutely would get us the moment of inertia of the Ford Fusion control arm that we're looking for. But that's a really computationally expensive way to solve that problem. Integration's expensive. I'll tell you that right now. I'm sure that might be a great thing to hear, because you're probably thinking to yourself, yeah, I could do 8 + 8 really quick in my head or on a piece of paper. Integration takes me all day. I totally agree with that. But specifically what I mean by it being expensive is that even our computers, relative to a simple linear problem, like an mx + b kind of equation, it's a lot more expensive to solve. So we're already got to be aware here that we want to solve our problem as cheap as possible or as easily as possible. And integration doesn't necessarily get us there. So what do we do about our control arm here? So we're going to play a quick game of Pictionary together. This is where you guys get to laugh at my drawing skills. So just consider any arbitrary block. This ain't a control arm. This is something else. And my mouse got away from me, so now I got to restart here. Boop, 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 boop. That was great. This is going on an auto part, but we have no idea how to describe this in math terms. And for now, let's go back to moment of inertia. That's the only thing we need to describe about this geometry in math terms. And rather than integrating it into infinitely small slices, that's what we do when we're integrating. We're treating things at at an infinitely small level. We're going to do it at a finitely small level. Hence the name finite element analysis. So I think we might agree the math could be hard to solve on something like this. You know, the von Mises stresses that could form from, 150 Newton load being applied directly on top of it. I think we could all agree that if this was a perfect square or a cube, that's a relatively trivial problem to solve. So how do we do that? Well, rather than breaking this into infinitely thin slices, like I said, what we're going to do as users is we're going to come in here and we're going to break this thing up into not infinitely small, they'll be kind of small, but not that small, squares and triangles. So what's happening is the idea behind FEA is to go from one complex geometry which yields, one complex equation in my mind. That's kind of how I think of that. Your CAD file on its own is a complex part, which is going to have all sorts of really complex equations to describe it mathematically. We don't want to deal with that because we want to solve our problems cheaply. So instead of one complex geometry, one complex equation, we're going to discretize it or split it up into still one complex geometry with, tens of thousands, hundreds of thousands, depending on the size of the model and what we want to do with it. Very simple equations. So we're still representing that same part, but rather than treat it as one big volume or one big surface, we're going to break it up into many, many simple equations, but certainly still a finite number of those. As a rule of thumb, the more of these elements we use in our meshes, the longer the problem is going to have to solve. And we'll see why that's the case in a moment here. But the reason we want to go to these simple shapes is because, like we mentioned before, we know how to quickly solve math. We have convenient formulas for a perfect square and equilateral triangle and all of these different things. And it turns out computers specifically are a great application for solving thousands of simple linear equations in parallel versus solving one extremely complex equation. It can do the linear equations much faster than it can the linear equation or the complex one, even though there's thousands more. So in a lot of ways, computers are a really good application, or finite element analysis is a really good application for the computer on what it's turned into. I'm not that old, I'm only 26, so I couldn't tell you how bad computers used to be, but we got some pretty good machines in front of us these days. And this is what they're doing. It's going through each of those shapes we've brought up, and instead of trying to treat each component or body in a macroscopic way, it's just going to look at one of those squares, solve what's happening at that square, and move on to the next one. And in that sense, load transfer in FEA is very much a propagation thing. So kind of looking at my claw here, if I wanted to apply a pressure downward on this top face of elements, and I'm just going to select the elements here. So I'm referring to this now white face here. Maybe we want to push down on that face. Well, what would happen is it would solve what happens at this element here that I've selected, and then it's going to push that down into this element, and so on and so forth there. That's really what's happening. And since we're kind of mapping this so small, the math works out pretty quick. It's a industry-proven and historically accurate way to do many different problems, including statics and dynamics and all sorts of structural and automotive parts. But I want to talk real quick here on why we ultimately need to go to simple equations and what those equations are. But hopefully this is starting to make a little sense here. So again, we want to go to simple equations because computers can solve those more, even if there's thousands of them, than the complex equation. But what's the equation we need to solve? What's FEA actually doing? And there's going to be different answers to this, whether you're doing a normal modes analysis for the dynamic behavior of part, or if you want to just do a pure linear static to see how a force will cause a part to deflect. Those might be slightly different things, but in general, what's going on in finite element analysis is something we've all seen before. It's essentially Hooke's law for an ideal spring extrapolated into a couple different dimensions. So it won't be just a simple 1D spring. Certainly you'll have to account for it in 3 dimensions. But that's the same idea here. And we're going to do a quick little mini lesson on Hooke's law to kind of really tie all this together here. So for those of us who don't know, Hooke's law is defining that the idea that any force you apply to compress a spring, for example, the deflection or the amount that spring's going to actually compress is going to be directly proportional to the force applied to compress the spring, assuming a linear stiffness K. So we got some deflection terms, we got a linear stiffness, and we have deflection itself there. Very straightforward. Now, it turns out FEA is just solving this equation, but sort of backwards. It actually has to invert it. And that's why I want us to think of this here for the rest of the week here. And FEA, a user defines this force matrix or vector, because again, it's doing this not just for one element, but all of those squares and triangles we saw on my crane model. It's actually solving Hooke's law for every single one of those and then moving on to the next one here. So what are the parameters of Hooke's law? Well, we have the force, and that's actually a user-defined parameter. You as users, and we're going to do this together a little bit more tomorrow than today, we're going to be defining pressures, loads, constraints. All of those different things are going to be things that we're responsible for defining. Likewise, you actually defined the stiffness matrix without realizing it. No, you don't necessarily go into every component and say, hey, this shovel on this, giant piece of machining equipment is exactly this many Newton meters stiff. There's ways you can certainly go about that, but stiffness is actually derived from a material definition and a property definition. And those are things we're going to go into a little bit more detail with tomorrow then. And then lastly, so we have two terms. We have one equation, one unknown. It really just inverts Hooke's law to be F over K equals X. This is a deflection of the spring or element. This gets turned into a displacement and a stress result. So that's all that's going on. What we're doing in SEA is we're taking apart a drawing file, a CAD part that we drew up in SolidWorks. We worked really hard on it. We did all the extrusions and the Boolean maneuvers. Looks really clean. It turns out that's a really hard problem to solve just on its own. CAD files have crazy different geometry file formats. There's all sorts of ways you can define the same 10 surfaces. So rather than have to go into the world of really complex surface equations to solve Hooke's law in, FEA admits that that could be a mathematically challenging exercise that could have a lot of inconsistent results. So we're going to just break things up into many, many small shapes. Turns out small shapes have easy math to work with, and we're going to solve complex math problems as a series of very simple equations. And through that workflow, we can determine, yield stresses on all sorts of auto components, do dynamic analyses, work with moving parts. There's a world of physics problems we can simulate and find an element analysis. And I just want to make sure that we understood, before we get too far into meshing today, why we need to do this. And the biggest reason we need to do it is that it's a mathematically expensive problem to solve. But if you just break it into simple equations, your simple shapes, it gets a lot easier. And if anyone ever asks you what's going on in FEA, you are not wrong if you just tell them it's Hooke's law. Someone might laugh at you and say that's not a complete answer. I would tell them to go shove it. You're welcome to do what you want to do. But really, it doesn't need to be any more complicated than that. And that's where we're at with this. So hopefully that kind of gives us some traction here for those of us that maybe have had some other, what's the word I'm looking for, some experience with this that kind of helps fit your own narrative, that how you thought of it. We're kind of gonna, but I'm happy to kind of pick up with people as we need to throughout the week here. Now, with that said here, I want to talk a little bit about some steps we'd want to take with our geometry files as well there. And actually, before I get to there, I want to make sure we wrap up with our model browser there. I don't want to go too far here. So what I'm going to do here is I'm going to come back to my little crane model, and I'm going to go back to that component browser in my model browser. So I have my component tree open, and again, we're seeing all of those different components again. So what's going on here again is we have those two flags we were learning about. And we're going to remember that the flag all the way on the left, I turn everything off. The flag all the way on the left will allow me to review the geometry of each part. So that's the CAD entity of it, and the input that our CAD designer sent us. And we're going to remember that the flag, half of each component, if you would, is going to be the elements or the mesh that's associated with that part now. So it's nice that HyperMesh keeps those entities separate, And we'll see why a little bit more specifically that's the case, but I like to think of it as just it's a good way to keep track of what you started with and what you're going to turn into the computer to solve your problem and get these optimized results or these simulation results completed for us after the fact there. And some nice little quality of life things we can do though for driving a HyperMesh session. Well, as you've hopefully seen, as I left click with my mouse, one of those flags, you can turn that entity off. So for example, I could come into any one of these components and I could just start left clicking to turn off all of those flags and it will hide the geometry half of the component. Notice the mesh is still being left behind. That has a separate flag to turn off. Now, certainly, just like I'm turning off all of my surfaces or my CAD data, I can turn off with that same left click the meshes for these components by just left clicking that mesh flag as well to toggle that off. So quick ways to turn on your CAD, turn off your elements, vice versa, whatever's easiest for you to see at the moment. But some other shortcuts. If I select the component header at the top of the tree, I can turn everything on by leveraging these little kind of shortcuts at the top of the browser here. They kind of look like these checkboxes, like a blue eyeball staring at you real ominously. We're going to kind of use those guys to help us out for a bit here. Now, the first thing on the left of this little toolbar, just above the model browser, is a drop-down flag control. For now, I'm going to leave this to be on both the mesh flag and the geometry flag. Just note that we have some controls here to display everything to turn all of those checkboxes on or all of those flags on. You have a control to turn all of the flags off, and you can even flip the display state as well. So right from this little browser, you have some quick controls on what to turn on and off, like we saw earlier. I can do this individually or in a more global way as well there. And then one other thing as well is if I select, I got to come a little bit more to the right for it. Try to highlight it again. So I come up here again, I'm going to come all the way to my right side. There's kind of there's another one of those scary looking eyeballs. One of them's got a plus minus, one of them has a 1. These are two tools that are toggled controls. So I'm going to left click it to turn it on. You'll see it's kind of like highlighted orange now. The one with just a number 1 allows me to isolate a component. Click to isolate it, nice and easy. Or likewise, the plus minus tool works in a cool way where I can right click a component to hide it, or I can left click over where that component was in the display, kind of like referencing a ghost almost. You can left click to turn it on. So short answer, a lot of your display controls on what you're seeing in the software is all managed from the model browser, specifically within this component tree. You can turn things off individually, or like we just saw, from the very top of that browser, there's a couple other controls to manipulate what's coming in and out of the software, or excuse me, in and out of the display state. Now, the final thing I want to mention before we move on to working with geometry files, won't be a big section there, just a few tricks I want to show us. I want to talk about kicking things out of the software and bringing things into the software. So back to the very beginning here. We talked about these HM models that we can do a file open to bring those in. So generally, if it's got a file that ends in .hm, we should be able to do a file open. I believe there was a question in there where someone was having issues. That's probably a version compatibility issue. So I'm going to make sure we upload tonight the 2019 package as well, just to avoid those issues there. But there's a few other ways we can bring other files into the software as well. And the first major of those ways is actually through import. So I mentioned earlier, if you
Garrett,
bring
I just
down
want to add that the student edition does have some limited capabilities of importing different files based on that. So the full version doesn't, of course.
Yeah, so we're happy to work with you guys on confirming if you have like a particular solver input deck file or a particular geometry file or something else coming out of a package. We're happy to check with you guys if we have the appropriate readers available to you. That's a great thing to check in with the support staff for. But what are the types of things we can bring in with the import here? So traditionally, in my mind, there's really 3 major files that we're going to be concerned with that you can bring into HyperMesh. So the first of those is very straightforward. We've seen it already. It's a model, so you can always import in just like you open a HyperMesh model. We'll talk about the difference in a moment. Now, likewise, you can also import in a solver deck. So we'll see this in action a little bit more tomorrow. But the solver deck is what comes out of HyperMesh, and it only cares about the element information. So in a lot of ways, the solver deck file is the same thing as the HyperMesh model file, minus the CAD geometry that was saved in the HyperMesh model file. Now that you've meshed it and the computer can read how to solve the math problem in an easy way because you've meshed it, it doesn't need the geometry file anymore. Your CAD at that point has been replaced by something a little bit more mathematically friendly. And likewise, something we're going to get in a very good habit of, and we're going to see together in a moment, is we're going to want to import in geometry because I need a CAD file to start with. So what typically comes up in a WISE class at this moment in time would be, someone would ask me, well, what's the difference between a file open operation and a file import operation? And you're not wrong in the sense that they both bring things into the session. But why do we have an import model versus an open model? Why do we not have a file open geometry? The first technical reason has to do with readers. So file open always, behind the scenes, invokes the same file reader to look to those HM extensions. Each of these submenus here, import a model, import geometry, have a variety of readers that you can choose from to read the correct file. But a more practical reason to think of these as very different tools, open and import, is that file open will always clear what was previously in the model, whereas file import will always just add to the existing model. Let me show you what I mean by that. I'm going to come back to this little assembly here and turn everything back on. And what I'm going to do next is go to File, Import, Model. And I'm actually going to import in the next model we're going to see together. So I'm going to go to Import. It's already set to Model for me at the top left. And let me talk about what happened here. So it just opened up a little import tab for me. These little 5 green arrows are referring to some of the different entities we can import. I know that this first one is already set to import model. And if I hover my mouse over it, the little tooltip will come up to let me know that that's import model. Now what I'm going to do is click the little manila folder just under it to select the file I want to import. And I'm actually going to go to our Chapter 2 student exercise folder and bring in a model called Quit Mid-Surface. And I'm going to import this in. Now you'll notice it didn't get rid of my crane assembly. It just dropped this new little surface model, this blue thing, right in the middle of space, and it kind of had no regard for it. Like, it just sort of showed up, didn't knock on the door, didn't take off its shoes, didn't do nothing, but caused me some problems here. And that's okay. I don't want us to think that import is always bad. One of the key features that I hope we're taking away from this is that import is always, without any regard for you, and appending to the model. It'll only add things without clearing. Whereas, if I come here now and I do that same thing, I'll do File Open, and I'll get that same model, Chapter 2C, Quit Mid-Surface. I'm going to open this. A little message is going to prompt me to discard the model. So here I'll say yes, and now what it did was it launched a new session for me with only that new model in it. So rule of thumb, file open clears everything before it brings it in. Import doesn't do any erasing. Now, there's a lot of geometry tools available to us in HyperMesh, and there's a lot of reasons we could be interested in modifying or reviewing, or in some cases repairing geometry. And from my experience, there is the biggest variety of different things you can do in HyperMesh at the geometry level. And it also has the potential to be the messiest. But I don't want to scare people, because while both of those can be true, 99% of the time, you don't have to worry about your geometry. And I don't want to scare people. What I want to do instead is just talk to us about what are some of the things I want to be aware of? What are some good habits for me to build, or while I'm reviewing my model? What could that checklist look like? And that's what I want us to kind of think about while we're going through this. So before we go too far, if we were to go into our student PDF folder here, I'm going to actually pull up Chapter 2 Geometry for a second here. Now, this is a 111 page long slideshow for just Chapter 2. Likewise, the other sections are pretty large as well. And like I said before, we're not going to have, unfortunately, not all the time in the world to go through every single one of those slides. But I would certainly recommend to those of you with the time and those of you that are motivated to do so, give these PDF files a thumb through. If I find out you were reading, one of these, it took you 8 hours to get through it, I'm going to find you and I'm going to yell at you a little bit that you were reading it, in too much detail. But what I would tell you guys is, take a half hour, one day. You're eating your Cheerios in the morning, or right before you want to go to bed, you want to just get a little bit of work done. Take a half hour and just thumb through these slides here. There's a lot of, good notes here, for example, the beginning on the different files we support and the commercial product for different geometries to bring in. Talks about the different geometry file types we support upon export. So just like there's an import, there is an export. And what I specifically wanted to show us here with the geometry slide is there is a lot of stuff in this slideshow. And if I get down to slide 24 here on creating geometry in HyperMesh. We're going to see in a moment that there's a lot of tools similar to CAD packages in HyperMesh to create new surfaces, create new solids, create just single lines. But in no way, shape, or form would I recommend to anyone in this room here that HyperMesh is your new start to part design and geometry design. We're going to see, hopefully by the end of the week, we're going to feel pretty confidently that FEA can do a lot of great things for our design processes. Specifically, creating geometry is probably not that one tool set. So why I bring all this up is if you're going through these slides and you're thinking to yourself, man, there is a lot of slides on creating surfaces and creating solids. Don't worry too much on that. I would just kind of skip right through it. Or if you need to, if you're looking for some, substitutes to your CAD package, definitely check out those features there. But I want to get too caught up in those. But instead, what I want to do is talk to us about some of the things that are probably worthwhile learning about as you're going through this. Now, in FE or FEA, we've already learned here that we're going to traditionally start with a CAD package or a CAD drawing file. In this case, I had a little simple quit model to work with. And this is a 3D part. I know that might seem obvious, but we're going to see a little bit today and certainly tomorrow that FEA is flexible in the dimensions of the components it works with. It can work with both sheet metals or infinitely thin surfaces at a 2D level, as well as the 3D level here. But what we're going to learn about now is that oftentimes it's a shortcut to treat 3D objects as a 2D object. And where we can really get away with making that sort of assumption, and we'll see how it's not truly an assumption in a moment here. This is often done, though, for sheet metal parts, a lot of plastic components, or really anything where it is much longer and wider than it is thick. So in this case, where X is roughly on the same scale as Y, but both of those are substantially larger than Z. And like we said, this is commonly in sheet metal, many plastics, especially, injection molded plastic parts. We'll kind of treat as a 2D entity in FEA, even though it's a 3D object. So why the heck would we do that? What's the purpose of doing that? Well, I want to go back to our little short lesson in FEA here for a moment. And then I promise I'm done doing the lecture. I probably should have forewarned you guys. The first hour with me is the hard part, and then I'm done talking at you. We're going to get really good at using the software here. But we're right there. Knowing we got to do all this Hooke's Law stuff we talked about earlier here, and we're doing it at each and every single shape or element that we created on the mesh, this is going to be dependent on the mesh here, knowing that we have Hooke's Law. So what are the implications of what we talked about on the previous slide? A couple obvious things here that I want to point out to us. More elements means longer computation time because it has more equations. Smaller average elements, we'll talk about this in a moment, typically means more elements. And likewise, for each element, Hooke's law is technically calculated. I don't know if I want to be that strict on it. I don't want to. At each node, though, and that's the final little entity we got to learn about here. So I'm going to come back to my my little quip here, and I'm just going to throw a mesh on here. And again, I'll make this yellow to make it a little brighter for us to see. I'm going to come into my HyperMesh tool. We're going to see how all to do this together in our afternoon session in a moment here. And I'm just going to put a little couple layers of square elements on this guy. So I've gone ahead and started meshing this part. I've only applied elements to just one of the surfaces, and I'm going to zoom on that here. So each of these square elements, I know they're a little bit more rectangular, has four corners of it though, hence the definition of a square. But at those corners of an element, we refer to them as a node, and it's its own standalone entity. And those nodes have some relevance within the calculations as well here. But where I was going with this, and why we need to be aware of the nodes, is we're going to play our last game of Pictionary together. And at that point, I promise you, cross my heart, all that good stuff, I will not bother you about theory again here. But the last thing I have to talk to us about is when we can get away with modeling something as 3D as 2D. So we're already kind of starting to think to ourselves that sheet metals and plastics and generally things that are thin, and the terminology you'll hear often are thin solids, is that we're going to model them not as 3D but 2D. And why we might want to do that is just to reduce solution time. This might seem trivially, really obvious, but it's still a very good shortcut and a very good thing to remember. So if we wanted to model anything in 3D, we would need a 3D element. We would need cubes or pyramids or something that exists in 3 dimensions to solve math on. And we know that your typical 6-sided cube is an 8-cornered entity. And so this is an 8-noded cube. And its 2D counterpart, just the flat, infinitely thin square, is a 4-noded little guy there. So right away, if we can get away with modeling something as 3D, as a 2D body, we're going to reduce the node count necessary to model that using our elements. And essentially, we have to do Hooke's law for only half the number of equations. We don't have that many nodes or sampling points or data points, however you want to think of it, that we need to calculate results for. We went from 8 equations to solve to 4 equations to solve for every element. And these models could be as big as 25,000 elements to 2.5 million elements. So you can really see those time savings there. And one other thing I can say to that as well here is that as your solution time gets more complicated, so for a lot of linear static models that only take up to an hour to solve, 5 minutes or 20% or some of those time savings don't seem that big on something that's only an hour. But some of these more complex models you can build in finite element analysis, like a crash analysis as an example, those could take as many as the 2 weeks to solve for on a computer running day and night. So if you're talking about saving 50% runtime, that doesn't always have to be an hour to a half hour. That could sometimes be 10 days to 5 days. And you could really see some time savings. So engineers are always looking for excuses to reduce those times there. And this is the easiest example of that shortcut. Now, how do we actually get away with, though, of modeling something as 2D? It exists in 3 dimensions. We can't just lose the thickness dimension of the part. I can't just say something was once 1/4 of an inch thick, but screw it, it's now infinitely thick, or infinitely thin rather, and we just lost that 1/4 of an inch of mass. That's certainly not the case. It's a smart approximation, and what's going to lead us into this is this idea of a mid-surface. So the first geometry tool we're going to learn about today is a very simple one called our mid-surfacing tool. And what this is going to allow me to do is I'm going to demonstrate this in action here. Don't worry about following each individual step for a moment. The mid-surfacing tool allows me to take a 3-dimensional solid that has a relative, uniform thickness. Hopefully it should have a uniform thickness. And what I'm going to do is I'm going to hit extract to pull out the middle surface, or the infinitely thin plane that would lie at its halfway point. So I'm going to set the 3D object to be gray for a moment, and the mid surface to be this bluish color, or maybe I'll go back to yellow there. And I have some transparency set as well. We'll talk about visualization controls in a moment here. But if I kind of set this in a side plane for a moment and zoom in.
Garrett, maybe I missed this, and sorry if I did. Could you explain how you're zooming with your mouse and panning and so forth?
Totally, not a problem there. Yeah. So yeah, we're going to take a step back here, and actually navigating the interface itself here. So we talked a little bit about this component browser, my model browser here, and how we got this big list of things there. But at a very basic level here, if I zoom back out here, I'm going to steal a little slide from our Chapter 1 slideshow. And some of the slides I can call you guys out to that I would very much recommend reviewing is starting on slide 21 of your Chapter 1 Basic Student PDF. We do have the complete list of mouse controls here. So the first thing I want to call out to with the controls, it's funny, I don't have faces in front of me. With the live training, it's much easier for me to catch on people can't spin things around because I'm seeing everyone's face of total confusion. Here, I'm just assuming you guys are like upside down, like hands behind your back, spinning your models around, doing all that cool stuff. So certainly slow me down as we get ahead of things. But the biggest thing I want to call out with our controls is that you do need to hold the control key with the default scheme to spin things around. So let me talk about what I mean by that. So I'm going to bring my model back up here. Now, in order for me to zoom in and out, I wish you could see me. I'm just doing the scroll wheel on its own and nothing's happening. I use my mouse with my right hand, so that means I'm going to keep my left hand sort of near the keyboard. And with my left hand here, I'm going to hold down the control key on my keyboard. And now as I use that scroll wheel, we're going to see us zoom in and out. So very quick and easy to access that. And likewise, while I'm holding that control key down, if I left click and drag, I'm able to both set my center of rotation and spin the model around. So again, if you want to set and change that center of rotation on the screen, hold control, left click the graphics area, and it will move. It looks like a very small white square. It'll move your center of rotation for you to change where you're rotating the model. So as an example, I'm just going to set my center of rotation to the very far right of this model on this far corner over here. Left click and control, it's placed over there. Now we'll see that it will pivot about, and I know it updates a little slow, but it will pivot about that corner there now. So very flexible to work with. And what I do like as well, if I come back to my slide here, so we've kind of already seen that the left click can be using for rotations and setting that center of rotation. The middle button or the scroll wheel is being used for a zoom in, and the right mouse button, don't sleep on it. If you're still holding that control key, will allow you to pan the model in the existing view. So it might seem annoying at first that you have to hold down the control key to operate these things. One of the reasons for that is so that way you're just not accidentally spinning the model around, and it took you 20 minutes to get a view set up and hide the appropriate things to look into a channel, and then you accidentally rotate it. But it also gives you an excuse to keep your hand near the other keyboard shortcuts. And that's going to be something we're going to really dive into tomorrow there. Now, while I'm stealing you guys for some of these basics here, some other very quick things I can call out here. We do have some standard view tools available from that top toolbar here for looking at slide 22 together. So you have both your 6 standard views, including the front and back of each of those, but it also comes equipped with an isometric view and even a little tool here to flip the view 180 relative to the viewplane of your computer monitor. So if you want to see the backside of an existing view, you can always flip it with that reverse view option. And speaking of keyboard shortcuts, let's say you really like having this view set here. Well, if you hit F on the keyboard, I'll put this in the chat window for everyone. F for fit all is the keyboard shortcut to fit the model. So this will zoom in out to an appropriate level, so that way everything is visible in the model screen. So if you accidentally zoom way too much in and you got yourself lost, you have no idea what this patch of yellow is that you're looking at, you can always hit F to fit all and zoom back out to be that level. Or likewise, maybe you zoom out way too much and you lost your model and you don't know where it is anymore. F to fit all will fix that zoom. And another one there is maybe you set this view up perfect, you got it fit all, and then you accidentally rotate and you didn't mean to rotate. If you hit B for back, we'll restore the view to the previous view before you had rotated or panned or whatever operation you had done there. So B for back. Now, it doesn't go super far back, just those two views you can toggle back and forth between, but a very nice tool there. If you accidentally rotate and want to get something reset up, you can always hit B to go back to that there. And we're going to learn a lot of those along the way here in our lessons. Now, a couple other final things here. So we've talked about rotating the model. We've seen these standard views. We know we can fit it to the zoom or go back to what we saw. But how do I actually change how it's being displayed? So far we've seen how I can control through the component browser whether a component's being displayed at all or not at all. We've seen that we can change the view that they're in, but I really don't have much control that we've seen so far outside of changing the colors of how these things are being displayed. And that's where I want to talk about our visualization toolbar for a moment here. So Darius, thank you for stopping us when you had, before we'd gotten too far away from some of this stuff.
Yeah, I know, Card, when you get excited and you're showing a lot of things, we jump into different areas. But yeah, I just wanted to make sure, because actually there was a question that came up about the mouse controls too, but that's because we're, going along quickly here. So, but no, but thanks for showing it.
Yep. So like we said earlier, we learned that we can use, at a basic level, these different flag controls from my model browser allow me to hide my geometry or the FE. Now, in this case, we have no elements created, so that's not going to have an influence on the model yet. We've seen that for the top kind of toolbar, we have all these different planes we can set the model in. But how do I actually change what these things look like beyond the color of something? And that's where this visualization toolbar is going to really help us out. So the visualization toolbar is on the underside of the graphics area. Bring my little spotlight back up. What we have here is kind of two halves, and I hope we're noticing that kind of that theme here, where I have one half of it is associated with only the geometry or only how the CAD's being represented, whereas the other half of it is likewise going to be the FE half of it, the finite elements, or just how are my elements being rendered. So for now, I'm only going to focus on the surface rendering half. And what we have here is a drop down that adjusts the coloring mode. It should be default to auto. And then we have a couple of tools that would control for the wireframe display, the surface shading, and even the transparency that's applied to the body here. So one at a time here, I can see that there's different ways I can color my component. Those are for example, by comp, which is short for by component. This just means whatever color is assigned to the component color in the browser, that's the color I want you to make it. But we also have one that's called by topology. We'll talk a little bit more about that tomorrow there. I want to stay out of the topology lessons today. But we also have some other options in here, like a mixed or a mappable even option, which we'll get into a tiny bit tomorrow for 3D elements and a little bit more specifically. But it's nice to know that there's other ways you could group or color your different components there. But might be more practical than just adjusting the color scheme, because I think we'll all agree that we're going to typically be doing this from a by component sort of address. It can be helpful to maybe render a body as a wireframe geometry, as I've done here, where it's only showing me the skeleton of it. Sometimes it's helpful to show the surface is shaded in, certainly, but maybe without the edges highlighted. So that way it's just more of kind of just this big blob without, letting me know where one surface starts and another ends with the surface lines that we can reintroduce. And we also can even apply transparency to these to make it easier to see through them. So again, in order there, we had the color mode, the wireframe, and there's various other sub options of types of wireframe geometry you can apply. Same thing with shaded geometry. And the last one there is this transparency view. And I like to use the transparency tool actually as an excuse to talk about how we use the panel areas in HyperMesh here, which is kind of our last very, very basics of HyperMesh intro lesson here. So what I'm going to do is I'm going to actually toggle that transparency tool here. It's that little kind of bluish box. Now, as soon as you launch this tool, you'll notice my panel area. I refer to this little this gray menu underneath the graphics area, just under all these toolbars. This is our panel area. And all of these little kind of yellow menus, in this case, I have a little yellow panel called components. We're going to refer to all those boxes as a panel. So how these work is any yellow panel is requesting user input. What kind of user input it's asking for will be in the name of the panel. So let's use some logic together here. I'm looking at on my screen here, I have a yellow box listed comps, short for components. This is a panel or a menu that's expecting me to supply a user input of other components. Now, for reference, this is that transparency tool, so it's probably asking me which components do you want to apply transparency to. Anytime it's highlighted teal, got that teal border to it, that lets me know this is the active panel. So anything I start selecting from the graphics area to add as input is going to be stored into this panel, if you would, as the input. So which components do we want to make transparent? I'm going to select a component from the graphics area. I can just left click. It'll highlight it white to let me know it's selected it. And now what I'm going to do is just use this little slider bar on the transparency side to adjust the levels of transparency. So I can go all the way to the right to have it be fully transparent, fully to the left to have it be completely opaque, and along the way you can give it, whichever degrees of transparency you're looking for. Once you're all set, you can hit return. The panel area has been restored. Now, it's typically a little more practical to do that. There are at least transparencies, I would imagine, on your 3D objects as well there. So same thing, I can go back to my transparency. I got that same component. It's a yellow panel, so it's asking for user input. I'm going to select the component and apply the transparency. Now, there's a lot of times some other controls onto these panels, and it's not just a simple one to apply a transparency for. Some things I want to point out for now before we expand on this. This little arrow on the right side of the panel next to components is clear or clear all. It's pointing to the left. It kind of looks like a rewind button on your old school tape players and CD players. So I can hit that little rewind button, and what that'll do is it'll empty the selection of my current panel. So it deselected the one component at the moment. It's a nice way if you accidentally started selecting a bunch of stuff and realize you were wrong and don't want to individually deselect it, you can always clear it and the mess. Now, likewise, if you only wanted to deselect one thing, just like left click from the graphics area had selected something, I can right click to deselect it from the selection. So anytime you're adding something into a panel selection from the graphics area with a left click, you can always right click to deselect it as well. Now, sometimes it's quicker to grab many things globally than to try to select them individually. So if I were to, and I'll even do this here, I'm going to go all the way back to my qual model. You guys remember this guy. We saw him together. I'm going to come all the way back to this little guy. And I'm going to go to that same transparency tool. And while I'm going through this, you might be thinking to yourself, man, that's a lot of clicking to apply transparency to everything to have to go through and one at a time click all of those different components. As a rule of thumb, if you have to select any number of things and you clicked more than a dozen times in HyperMesh, you weren't leveraging a shortcut that could have saved you some time. So in this instance, if I just want to grab everything, a quicker way could have been to do a window selection where I click and draw a box around the parts, let go, and it selects everything in the box. How I had done that was I held Shift on the keyboard, and while I was holding Shift, I left-clicked and dragged that same left-click to grab a component, and I can simply release them both to release that window selection. Now, maybe there's a little bit more specific you want to get than just some things in a window. So another thing you can do is you can actually click the panel itself to introduce some new shortcuts. So we're going to see as well over the next couple of days together that when I click my little yellow component panel, it brings up an entire list of components for me. So maybe I just want to grab everything that's got 3D in the name. And I'm only going to select these components. I'll hit select. And now what that's done is that gave me a particular way to only apply a transparency to just some components. So just be aware that clicking the yellow panel itself can also bring up a whole range of different shortcuts there. And that's something I wanted us to be familiar with throughout the week there. And we're going to see plenty of different panel menus, but the biggest thing I wanted us to be aware of for now is that yellow panels are ones that are looking for user input. You can get user input from the graphics area, but we can also go ahead and use the panel itself if we select it to introduce some shortcut methods. Now, speaking of shortcut methods, where does that put us with that previous clip example we've spent a little bit of time on here? Where we were at with this was talking about this idea of modeling 3D things with 2D elements. How is that the case? Well, if I come back to my little game of Pictionary here, the idea behind it on why we're interested in doing this is essentially that 3D objects are more expensive mathematically. A cube with 8 nodes is going to be roughly twice as expensive as a 4-noded infinitely flat square or a sheet. But how do you actually model something as 3D though if it's only 2D? And the answer comes from this idea of an analytical thickness that we can apply later. So what happens here is my length and my width and my thickness on this cube over here all equal, let's say, just 10 millimeters. This is a 10 by 10 cube. This is 10. I'm sure you guys love my handwriting. 10 by 10 by 10 millimeter cube. This guy over here is only 10 by 10. So where do we get that third dimension from? Well, we're going to actually apply it analytically and save ourselves some time. So how it does that analytically is if this is that that equivalent square, what's going to happen is we're going to apply a thickness property. I mentioned materials and properties earlier. And rather than literally modeling something as a cube, we're just going to model it as a sheet of paper and say, that's a sheet of paper. But if you apply this thickness to it, and it's a 1-parameter property, that'll just be a thickness value, just give it a couple millimeters on the top and bottom, and we'll call it a day. So by default, you can always take a 2-dimensional element, and with the correct property card that we're going to learn how to apply tomorrow, you can turn it into a 3D object there. And that's where, going back to the beginning of this lesson, I wanted to get us with this idea of mid-surfacing. So what we can do, pardon me a moment. Oh, I think the dog just got home, actually. Got to keep things a little quiet for him. What I'm going to do here with this part is I'm going to come into my geometry menu. So one of the things we're going to learn right away about HyperMesh is if I come down to my panel area, all these gray boxes, there's a little radio menu on the right of them. I think of these as menus or pages, and we'll notice right now it's turned to my geometry page. I can cycle through here to like 1D, for example, 2D, and so on, and there's a variety of different tool sets. Naturally, when we're in geometry, or when we're starting, we're going to typically work with our geometry tools in the beginning, and we're going to see how going through this, we're going to kind of use a combination of 2D or maybe even 2D and 3D elements. Perhaps we'll need some 1D elements that we'll learn about tomorrow before we can go to the analysis menu and start creating the loads and the constraints and define the physics of the problem that we want to solve there. So different things.
Garrett, I just wanted to add a point. I know an example here, you're trying to visually help out there, but there are some rules to follow with what size your thickness should be in a model you use. So, again, there's the plate theory that you have to follow, which basically specifies your typical thickness to width ratio of a plate structure should be less than 0.1, and that's a rule that should be followed. So just to be careful that you wouldn't be applying the same amount of trying to make a plate model incorporate a large volume at that point, because you would be breaking that theory and the accuracy of your results wouldn't be there. But again, I know we don't have time to go into those details, but that is all covered in one of the free ebooks we have, which is on our website. It's called Practical Aspects of FEA. We go over a lot of the details in there and descriptions and a little bit more theory. So if you haven't taken an FEA class, thank you. You could go in there and it has this covered in there pretty well. It's again, this is actually quite extensive, so it's a good material to have to keep in your library on the teams there, so you can point people to that. So, but I just wanted to make sure that, because this does get a little confusing, especially for people who haven't taken an FEA class or dove in and done projects, what should be done. So just want to make sure we don't use plate models when we really should use solid elements.
Yeah, that was perfect. That was like perfect timing too. And that document that Darius had mentioned that I had pulled up, that practical aspects of finite element analysis, I was going to wait to mention that on our last session together here. But you can find that on altairuniversity.com under the free ebook section, as Darius had mentioned. That is something I read quite a bit about this before I joined the company in school at various research jobs. I still reference that document in my own day-to-day to this day, though, here. As generally for me, anytime I'm doing a new type of analysis or working with a different type of parts or a couple different caveats there, that's usually the first document I'll reference for myself, just to get the basics covered or know what questions I need to ask next. So, and I know when I was first joining Altair, I had a few sections of those chapters printed out. I don't think the facilities team was thrilled with me printing out like a couple hundreds of pages in the company printer, but it was very useful to have that on hand. And as Darius had mentioned, that's a combination of both theory and button clicks there. And frankly, of all the documents I've seen, whether it's something that Altair has made or another third party, that's the best marriage of those two concepts there, really helping you have a document to answer, what do I need to do and why do I need to do it? And it gives you both of those answers, when I think a lot of information tends to only give you one or the other. You're either doing it without knowing why, or you know why but not how. And that's an ebook there that I can really think help clear things up. And I'll probably honestly end up revisiting that together as our class and our final session there. But one of the topics, you can go into much more detail than what I provided us today for a shortcut on why we can get away with modeling things in a 2D, with a 2D element, even though they're meant to represent 3D shapes. And we are going to learn in a moment that we can do this in the property part, but I want to talk about some of the geometry tools that we can do to help us with this. So we saw earlier, if I come into my geometry menu here, I can go to this little middle column that tends to be organized. So this middle column, we're going to notice is for surfaces, whether it's creating new surfaces or editing existing surfaces. And there we have this option called mid-surface. This tool allows me to select any 3D solid or enclosed volume of surfaces, and like we saw, pull out that middle plane. So if I kind of set my view here for a quick moment, there we go. I'm going to set some transparencies as well. A little too much transparency. It's not the easiest to see here. I'll try to get it a little bit of an offset. But hiding in that outer surface there, which I'll make a very dark orange, and the inside I'll make a very bright white, is just an infinitely flat plane. And if I turn off the outer component, what's left here is just a flat plane. You know, this was once a 3D bracket, but if we zoom in, it has no thickness. It's just an infinitely flat surface. Well, that's okay. The meshing tools are still going to behave the same, and we're going to see in a moment here together how the meshing tools allow me to take a surface like this. And let me change the color here just so we can see me selecting it while we're going through this. As I'm selecting surfaces, it's still going to create elements for it. We're going to talk about a lot more in depth with meshing techniques and how to choose an element size tomorrow. In a moment, we're just going to get familiar with the basics of this tool. But if I just throw on a generic mesh here, so I just went with a 5mm mesh, it's going to give me 2D elements. And when I'm done with it and I only display my elements, well, I still have that same problem. It's only an infinitely thin part. It's almost, you know, it's no thicker than tissue, piece of paper. How can this possibly model a 3D object that's stiff, that can dent, and it's going to provide me stiffness? And we do this through an idea of a property card. So our goal oftentimes in FEA is to be able to do simulations that would be otherwise too expensive. And crash analysis is a really easy way for me to think of that. It's expensive to get the sheet metal and the labor costs and everything else to design, you know, half a vehicle just to put it on a sled, get it going 90 miles an hour, and run it into a barrier. That's thousands of dollars. If you can do a computer simulation that's just going to cost you a couple $100 in labor and the share of the license, that's certainly a big money win there. And in FEA, we want to be able to do those as cheap as possible. And that's why we want to go over this idea of this shortcut here. And this shell property here is what allows us to make what we might refer to as the digital twin. Because one of our goals in FEA in order to solve those problems is we need to make sure we're representing the part as true and honestly and accurately as possible in the software. Otherwise, we don't have an apples to apples comparison anymore. I get an apples to oranges. And I think for all of us working in, I'm going to keep using automotive safety as my example. If you're working in crash tests, you really want to make sure that the results you're running on your computer are the same vehicle and are going to be as accurate as possible because, well, you're probably driving that car home later. You're selling that to someone, and you want to feel confident in those results there. And right away, I can understand how using these 2D elements can give you that bit of apprehension that we're not getting that most accurate model here. It seems like we're getting closer to an apples and oranges comparison than apples to apples. But if I come in here and I model this part with that appropriate thickness property we're going to see together, and naturally HyperMesh does have some basic geometry tools here. One of the quality of life tools I can call out here. If I come into my spotlight tool here, we have a little tool hiding in my geometry menu called length, and that second column to the left. This just allows me to pull out the length of any given line on my part. I'm going to use this to actually extract out this particular geometry line here, which defines the part thickness. And it's going to let me know that that's about 9/10 of a millimeter, 0.91 millimeters thick, probably in inches if I had to guess. We'll just call it 0.91 inches here. So I'm going to need to create a thickness card that lets me know all those elements we created had a particular thickness. So I'm working on a property card. We're going to learn all about the different other varieties of properties a little bit more tomorrow. And I'm going to model this guy with a 0.91 thickness, and nothing really happened there. And it feels a little underwhelming. But one of the cool things we can do in HyperMesh is using those same representation tools or those rendering tools we learned about on the underside of my graphics area. There's a little hidden option here for my element representation. So I want to talk about element representation now that we're familiar with surface representation. Like we saw before, there's tools in here to first describe how we want to color our components. I just renamed or rather recolored this component to be yellow, but of course you can assign it to be the color of the material assigned to the part. You could assign it to be the color of the property card that's been assigned to it, or even things based on thickness or a configuration. There's all sorts of different ways we can color these components. I'm going to go back to a color system of just by the component for a moment But likewise, we have things like transparent elements or wireframe elements, shade them back in without the mesh line. There's all sorts of ways you can render these. But I think more practical than any of those, kind of hiding just a few more options over to the right, it looks like a gray flat sheet. What this is our 2D element representation. If you pull this drop down open, I'm going to choose this option called detailed element representation. And what this allows me to do is actually see how those aren't actually infinitely thin elements. They're meshed as infinitely thin, but by the time the solver sees them, once this model is exported and actually being solved for, the calculator is going to know to actually treat those as elements that are as thick as we're seeing them here in this detailed representation, and it will generate the stiffness for them after the fact. So I mentioned before in our theory lesson that we're solving Hooke's law for each element. F equals kx, we invert it to be F over k equals x. X turns into a displacement and a stress result. And I mentioned to you guys that in this equation, S and K were user-defined parameters, K representing the stiffness of any given element. How is it deriving the stiffness of those elements? It takes the shape or the area of the element and it applies the material definition, which will have a Poisson's ratio, a Young's modulus, and all that jazz to it, as well as the property definition. And in this case, the property definition has the thickness. So it takes an area multiplied by the property card, gives it a volume, applies a material to the volume, and all of a sudden you have a digital representation of an actual part. That might seem a little confusing. I'm sure I lost some of you. I apologize in advance. This is going to make a lot more sense tomorrow when we see this in a little bit more detail. But the property card is what's turning a mesh on its own to being just a really fancy geometry file into a digital representation or virtual representation of your actual part. On its own, a mesh is just geometry. And the only reason we made the mesh was to make the math simpler. It's the materials and the properties that give it that life, that actually give it stiffness or physical meaning on our computer then. And what's really great is not only do we have a tool, that mid-surfacing tool we saw to quickly turn those thin plated solids or thin solids into a mid-surface, but we also see that the mid-surface, once meshed, it was very quick to just create the appropriate property with a single thickness value and then turn those flat elements into not just paper thin, but actually have volume and stiffness to those tools. So when you're going through the geometry tools PDF, I mentioned to you guys earlier, this was a behemoth of slides in here. There's certainly worthwhile things on working in different unit systems and importing those unit systems in. We're going to kind of put the topology lessons on the back burner. I'm going to talk a little bit more about that tomorrow here as we get deeper into meshing. But the other couple things here that I would want to mention to you guys is that there's a lot of surface and solid editing slides in here. Definitely as you need to review those one at a time, but mid-surfacing is as common as, it feels like it's the PB&J almost in my mind, of finite element analysis. There's certainly applications you will never have to mid-surface or it won't make sense to, or you can't mid-surface, but it's an extremely common way of working with 2D elements there. And the final thing I can say to it is, given the name, that mid-surface will always lie upon the middle part of that thickness direction of any given solid. And naturally, since it's at that halfway point, the thickness that's applied to the elements through the property card doesn't apply all of the thickness on top or all of it on bottom. It applies half the thickness on top and bottom there to account for that fact. So it's a very flexible workflow for you. And we're going to remember that why we took the time to talk about this idea of a mid-surface is that it saves us time. Well, let me be more careful. It doesn't save us time. It probably took us 5 minutes to make it. It saves your computer a lot of times. And one thing you're going to hear me say more and more throughout our sessions together is if it costs you an extra 5 minutes to save your computer's 2 hours, pardon my language, but damn right, you're going to take those 5 minutes to save the computer 2 hours. I'm a big fan of what I refer to as deliberate modeling, and that can be painstakingly deliberate or redundant sometimes in my mind. I know some of our newer guys have given me a hard time for trying to get them to go very diligently through some workflows when I'm training them up. But in my mind, we really want to avoid an FEA. And when we're getting into some advanced meshing tips tomorrow, we want to try to avoid any situation where it's 1 step forward, 2 steps back. We always want to be 1 step forward, the next step forward. And we're going to always be looking not just to be deliberate that way, but anytime we can spend an extra 5 minutes to save 2 hours down the road, we're generally going to want to look for those time savings. And back to those shortcuts, we're going to remember that by cutting 3-dimensional things up into slices rather than cubes and just give it an analytical thickness, that's going to save you a lot of time in solving steps. So when you're waiting for your results, this is a very quick way to ensure you have a much smaller weight by going to take the time up front to generate a niche surface. Now, that's been a lot today. We got a little bit of theory. We got a little bit of just navigating the software, what we're looking at, and some practical reasons of using the tool. But before we really dive into different types of meshing tomorrow and applying loads and boundary conditions, setting up these results, I want to talk to us just about basics of meshing in general. And specifically, I want to talk about our auto mesh tool today. It's kind of the basic level. Most of our meshing tools are built from that in some degree. And really just make sure we feel confident that as we're clicking on things, in our own time, we know how to make these elements and how to adjust them while we're going through it. So what I'm going to do is I'm going to close this model, and I'm going to open up in our chapter. There'll be chapter 3, 2D meshing. I'm going to open up 03A. It's a sample surface mesh. Now, if we were in a live training here, I would have a little competition with you guys. I'm always curious what people think this part is. I've never been confirmed from our content team on the folks that made this training module. I think it's a heat shield. If you have a better guess, I would love to hear it. I've heard some people also call it the Batmobile. So if you want to think of this as the Batmobile, where you kind of like squint and it sort of looks like the Batmobile, I'm not going to stop you. Whatever gets you excited to mesh the part though. But we're going to notice right away, whether we think it's a heat shield, the Batmobile, or something else, this is a thin solid. It's already been, excuse me, not a thin solid. It is a mid-surface. This has already been mid-surface for me, or at least it doesn't have a 3D component to it. This is only a 2-dimensional entity. So as a rule of thumb, when you're working with surface data, not solid geometry, you almost always have to assume you're going to be applying that thickness property after the fact. Now, I want to go about meshing this component though, and we're going to talk a little bit more about the whys and the thought processing and meshing smarter, not harder kind of platitude stuff tomorrow. Today, I just want to make sure that when we leave today, we at least know the operation order in order to make sure we're generating elements. So what I'm going to be concerned with here is in my panel area, I'm going to come down here and I'm going to set this to my 2D page. And from my 2D page, there is a boatload of tools. And hiding in the second column to the right, at the very top of it, is a greatly appreciated tool known as the Auto Mesh tool. For you keyboard warriors, put this in the chat window. The F12 key is the shortcut key to launch the Auto Mesh tool. So if you don't like having to take your mouse hand, bring it all the way down, switch to the 2D menu, bring it over left to Auto Mesh, if it's faster for you to just hit F12, that'll always get you to the same place as the button clicks. Whichever your preference is, I don't want to force people into mouse controls versus keyboard controls. Just want to make sure we're aware of the options available to us. Now, right away, I'm going to call out in our panel, we have a yellow panel that it's requesting. And we learned from earlier that when we see a yellow panel, that's requesting user input. Typically, the what do you want me to operate on? So we know this is the meshing tool. It's going to turn my surfaces into squares and triangles to do math on later. It wants me to select surfaces here. So I can come in here, and we learned a couple new ways together. I can either individually click some surfaces, and you'll see how inaccurate I am with my mouse pad. For anyone who plays CSGO, you do not want me on your team. I have no mouse control or bad mouse hand, no good aim. You don't want me on your team. Now, I said earlier though, if you click a lot, you're probably not leveraging a shortcut. And I can already hear someone screaming at me saying, do the window selection. So certainly I could come in here, hold shift. While I'm holding shift, I can select more stuff, or I can even leverage a shortcut from the yellow panel menu when I will click the yellow panel. And all of these other shortcuts popped up here. I have options such as select surfaces that are all displayed, just select all of the surfaces, select everything on a particular plane, select things by the component that it belongs to. There's a variety of selection shortcuts you can experiment with. What I'm going to do for now is a very common one I do. I'll click the yellow panel, I'll come over to the left column, and I'll just hit all. What this is going to have me do is just select everything in my model, whether it's displayed or not. And now that I have all that selected, I can actually use the meshing tool itself. The meshing tool, once you supply it surfaces you want to create the elements on, the only other input it needs from you is to know how big those elements need to be and which type of elements they should be there. So we're already introducing a couple of questions that we want to ask ourselves. I'm going to keep it simple for now, just use an element size of 4 or 4 millimeters for this model. And for mesh type, you're going to see there's a little drop-down menu just next to it. It's that little arrow pointing down. I can open this up, and there's a variety of different elements or shapes I can use. I could do majority quads, majority triads, a mixed combination of them that'll yield typically majority quads with about 10% triads, or even only quads in a variety of reasons. As a rule of thumb, once upon a time, I think there was more variability across the meshing tool. It wasn't as mature as it is now, and there was a lot of valid concern for your triad to quad ratio. I don't want to speak for everyone, but I really feel that at this point, how far HyperMesh has come along since its first release, there shouldn't really be any concern for most analysis cases. I can always be proven wrong with one specific caveat, but as a good rule of thumb, you should feel confident for your 2D meshes using a mixed mesh type. There's technically a mathematical concern that due to its shape, triad elements are artificially stiffer than a quad element for an equivalent edge length, just given how a triangle is oriented compared to a square. Those differences at this point, the solver has so many checks built into the solution to control for those artificial stiffnesses. It's really not something I would be concerned with. I'm happy to go into more detail. We'll see tomorrow some other use cases for the different mesh varieties. But if you don't know of a reason, or someone hasn't given you a reason to use a different mesh type, you should feel confident and comfortable defaulting to the mixed mesh type. I don't know where this fear of triads came from. I'll have customers come up to me that were telling me that they hate their triads and their meshes, or someone told them they can't have them. That's such an overstatement. It's simply just not true in that case. Don't be afraid of your triads. If I find people using the quads only, and they can't tell me why, I'm gonna smack down the hand with a little bit of a rule or something. I don't know. I'll never see you guys. I can talk all the smack I want. Now, with my mixed mesh though, here I have just gone ahead and selected all of my surfaces like you guys saw before, threw my 4 millimeter mesh onto each of those surfaces, and this got broken up into all sorts of different stuff here. There's a lot going on. The great thing about HyperMesh is that meshing on surfaces is interactive while you're doing it. And this is what we mean by that. So I know there's all sorts of like glowing yellow orbs and numbers written all over the screen. It's kind of looking like you're slowly like devolving into the matrix here. And that's certainly not the case, fortunately, or I guess unfortunately, if you're really into that. I'm going to go, fortunately, I'd like to not live in a world ruled by machines. But I want to talk a little bit here about what's going on with these. So I'm going to go back for a moment. And we do support Control-Z or undo in HyperMesh as well. So this is an excuse for me to just Control-Z to go back. And I'm going to go back to my mesh tool, and I'm just going to mesh one surface this time. We're going to start simple. I'm going to mesh just this little surface fillet over here. I meshed it, I hit OK, and now what I'm seeing is the green mesh before it's finalized. And I see a couple numbers on the screen. I know it's probably tough for you guys. It doesn't let me change it as I zoom in. The numbers being shown on my screen here, I'll pull up the PDF slide to help me out, call these out for me, is what we refer to as the element edge density, or the node density on an edge there. Element and node density are typically used intertwined, though technically node density would always be one higher than your element density. And this is what I'm referring to here. They got a nice example of it on slide 6. So what the heck is all that 5 referring to? That 5 is referring to the number of elements that are going to be placed along that edge. So in HyperMesh, the meshing tool actually isn't that fancy. It does some cool things behind the scenes, but the basic logic of it's really straightforward. It takes every given edge length on the surface that you've meshed. So I got 4 edges for this simple fillet here, top, bottom, left, and right. It takes however long that edge is and just divides it out by your average element size. So let's say you had a 30 millimeter edge that you wanted to mesh with 10 millimeter elements. Well, it can figure out very quickly that 30 over 10 is 3. It can fit 3 elements comfortably along that edge, and that's what it's showing me here. So HyperMesh has figured out that if I want to do an average of 4 millimeter elements or so, it could comfortably fit about 7 on the top edge. Due to the radial difference on this edge that it's got a smaller inner radius and an outer radius, it wants to do 6 elements on the inside, and it's going to do 4 elements in that radial direction on the left and right there. So right away, it's just taking your edge length, divide it by the element size, and figure out roughly how many elements it could fit for that given size there. Once it has that outer perimeter mapped out, it's just going to use the element types you provided and find the most optimal way to arrange the shapes on the surface. So where I'm going with that is just remember that meshing within HyperMesh is done exterior inward. It starts with those edges, and then once it locks in the edges, it just fills in the rest for you. So you really shouldn't be too concerned with while you're going through here, oh man, I want to change that one individual element shape. A better way to think of it is just in terms of these element densities, and I think that can really simplify the number of things you have to worry about. Now, one of our goals we're going to talk quite a bit about tomorrow is while we're meshing is that we want to mesh in a way that gives us mesh uniformity. And there's a couple different ways we can think about mesh uniformity. The easiest of those being that all of our elements look the same as their neighbor. In FEA, since we took one part and broke it up into thousands of simpler shapes, it's important that those shapes be as comparable to one another as possible. That's part of kind of modeling it as a continuum in FEA. It's one of the caveats of that assumption that we got to make. And it's sort of intuitive in the sense that you wouldn't feel confident comparing the results at elements that are about this big of 4 millimeters. And then if on that same mesh just next to it, I had something crazy that was, like 0.5 millimeter sized elements. I don't get a lot of confidence that the stresses I see on one shape of elements are going to be comparable to the others. Now, technically, the math has gotten pretty good in your solvers at this point. It can account for those differences in sizes to a fairly accurate degree. But you want to give yourself as best shot as you can to give yourself these apples-to-apples comparisons. So one thing we're going to learn about is that we want to be trying to do mesh uniformity, and that often as possible, we want every element in a perfect world to be the same size and same shape as its neighbor. That said, sometimes triads are necessary, but sometimes triad elements aren't necessary. Which brings me back to this situation here. Because of changes in length at the inner and outer radius of this fillet, HyperMesh determined that it'd be best from strictly an element size standpoint to only do 6 elements on the bottom. But I mentioned that meshing is interactive as well. So I can actually come in here and using a left click before I lock this mesh in, I'm going to left click the edge, which that bottom edge is, that only has 6. And as I left click it, it's going to increment that element count by 1. So that number went from 6 to 7. Now that it's been updated, I'm going to hit that mesh button again in the tool. And we're going to see that it remeshed it with this time 7 on top and 7 on bottom, and that gave me a much more uniform mesh. So I like to think of meshing only in terms of those element densities because A, it's starting with those when it meshes, but B, the easiest way for you to adjust the shape of a mesh on any given surface is to adjust those density values on the edges. So knowing that's what we're going to be working with, what we're going to learn a lot about tomorrow here, we're going to kind of dive right back into this problem here, is I want to show us a kind of a practical workflow on how we can mesh this part. And we're going to use this as an example to talk about some of the questions about determining an element size, some of the other controls we have for 2D meshing. And after, a good 40, 45 minutes or so, I feel like we'll have a really good exposure to 2D meshing. And that's going to put us in a really good spot to wrap things up with 3D meshing and even some of the analysis setup steps tomorrow for loading and constraints. But the final thing I have for us today is I just want to reiterate those interaction steps. So like we saw earlier, I can come in here and just select a handful of these surfaces at the time. I'm going to start small here and just do a little segment of maybe 10 or so surfaces. I've specified a 4mm mesh in my bottom panel area. We're going to use a mixed mesh type of mostly quads with the occasional triad if it helps out. And I'll leave the rest of everything else to its default settings. I'm going to hit mesh, or alternatively, for those of you with the scroll wheel on your mouse, you can click in the scroll wheel as OK or confirm. And now I have all of these edge densities to adjust. So if I left click up here, this top edge, I can adjust it from 10 or 9 to 10 elements. And typically when you have even numbers, or not even, identical numbers of your top and bottom edges to your left and right for boxy surfaces, HyperMesh will be good about maintaining a very orthogonal and quad dominant mesh there. It's when those element densities don't line up with one another evenly, it introduces a triad element to account for the transition area. So really, anytime you're trying to go from 4 nodes to 3 nodes, the only way it could do that across that area is at some point, one of those quad elements has to get shrunk down to a triad to manage that 4 to 3 transition period. And the left click of this mesh tool allows me to increment and adjust those densities. And just like you can increment it up with a left click, you can right click it to increment it down to also just say I want to use less elements on that particular edge or density there. So this is allowing you to come in here and not just, get clean mesh flow. There's a lot of other ways we can influence this here. So for me personally, when I'm looking at this tool, I'm trying to think of this as a way to give me as clean of a mesh as possible, so that way all of my elements are ideally as close to the same size as possible. But even more importantly than that, I want to make sure that the surfaces I'm getting here have elements that are all ideally the same shape more than size. So what I mean by that is I want my squares to be as square as possible. I want my triad elements to be as triangular as possible. And I don't want to see, stretched out corners or diamond looking quads or much longer than they are short quads. You want everything to be as uniform in shape as possible there. Now, before we go too far here, I think it'd be best if we just called it a day there, now that we've had a little bit of a chance to be introduced to 2D meshing here. And we're frankly going to pick right up tomorrow, taking a much deeper dive of using HyperMesh to mesh this part. Like I told you guys before, my biggest goal today was make sure that we knew, do I know where this UI is? Do I know some of the basics of the geometries we're going to want to do with? More than that, though, do I have enough of the theory background kind of in the back of my head, or know the right questions to ask here, that when we get into some of the questions that we're going to have to learn to answer with meshing tomorrow, things like what's the ideal mesh size I should use, or when do I not want to use a mixed mesh but a different mesh type, we're going to have to pull on some of the lessons we learned in this theory lesson here to help out with that here. So what I'm going to do actually for you guys is I will actually save this now. And I'm going to actually send this to you guys in the chat window here in just a moment here. So please don't leave yet. I just want to make sure you guys have access to that. So if anyone wants to review that one more time before they go to bed tonight, you'll have that in your back pocket there. Now, With that said, though, please certainly, I'm going to be hanging out for a few more minutes in the chat window if there's any questions that Darius or I haven't got to. But that said, Darius.
Yeah, there was one question, but I just want to add to the point about there with the mesh quality. As you will show later, that HyperMesh has a lot of capabilities to check for that. But the first check is just a visual check. Does it look aesthetically pleasing? A lot of times you can find those areas out, as Garrett said, with long stretched out elements which somehow don't look right. You can usually do that a quick check and get those done first, or modify your mesh density to fix that. But then we have a bunch of element quality checks that will help get it straight at that point. So there was a sort of a question that actually was really just wanting to ask you if you can re-explain the 2D mesh again when you do 2D mesh over a 3D mesh.
Yeah, so let me steal my Pictionary slide here. So what's happening there is I think it's clear why we would want to ever model something as 3D using a 2D element. And we know it just comes directly from 8-cornered element versus 4-cornered element. The 4-cornered element is going to be quicker to solve for, and essentially has 4 equations tied to it instead of 8, as a very rough-hand way of thinking of that. But how it actually goes about still accurately representing this has to do with how HyperMesh derives stiffness on any element, whether it's a 3D element, a 2D element, or we're going to learn briefly tomorrow about this idea of 1D elements as well. It's a straight line that has an analytical cross-section rather than a sheet with an analytical thickness. But what HyperMesh is essentially doing, if I come back into my model here for a moment, let me close this guy out for a second. And I'm going to pull up a 3D model here to kind of compare it to. So this is a part we're actually going to see tomorrow. So this part right here would be extremely challenging to model with the 2D approximation because there's no obvious way to generate that mid-surface to it. Sure, if I zoom into this little feature here, I think we could agree how I can, we'll play another game of Pictionary together. I might be able to, take a pen here, and yes, I can define that middle section right here and kind of outline this, and we could turn around and say, hey, this flat sheet that I'm drawing here, the black checkered line, should be some 5 inches thick, or whatever the heck that part dimensions are. But that's only in that one offset direction. This part is so awkwardly shaped. It's got thickness in every which way. It's not always going to apply that same offset thickness direction in the same way. Whereas if I come back to the clip that we were working on earlier, let me come back to this guy real quick. This component, yes, it's a 3D one, just like we saw with the previous much more blocky housing structure. But what's convenient about this particular 3D structure is that it is always uniformly thick in the same offset direction, if you would. It's not all of a sudden getting thicker in one of the other faces that it is in the others. This thing clearly has a constant and uniform thickness, or it doesn't even have to be a uniform thickness, is really as long as it's got a constant mid-surface. So the fact that just due to the geometry of the part, this allows me to get away with that mid-surface shortcut or approach with it. And one thing I hadn't explicitly said is that not every 3D geometry is going to be eligible for a mid-surface approximation or shortcut, if you prefer to think of it that way. And we're going to learn tomorrow with 3D meshing. There's a couple different ways to 3D mesh apart with 3D elements. There's one school of thought that's using only triad elements that turn into pyramids. There's another school of thought that starts with your basic 2D squares and triangles and pushes them into a third dimension. We're going to learn tomorrow that not every part is available for that second approach of extruding your 2D elements into the third dimension. There's going to be a couple caveats that come with that. Now, So hopefully it's a little more clear that why we could do a mid-surface on this component is the fact that it is always, that 0.91 inches thick, regardless of the part. Whereas if I went back to that other solid, coming back here, wrong folder, this particular solid, sometimes it's getting thicker in one direction and then not in others, where this arch structure too, you couldn't really figure out an easy way to get a mid-surface for it because it'd have to apply thickness in multiple directions. That gets really challenging. Now, how it's actually generating the stiffness correctly for that given volume has to do with how HyperMesh derives that stiffness. So really, what's going on behind the scenes is kind of list this out a little more clearly here. So we take a geometry file and we turn this into elements, and we call that meshing. But meshing on its own, like I said, is just fancy geometry. Doesn't have stiffness, doesn't have math. We don't know anything else about it. It's no more telling on its own, a mesh, than the original CAD file that you worked with. So if the mesh is meaningless in this sense, how does my solver actually solve the math problem, right? How do I actually solve my cantilever beam problem if my mesh of the cantilever beam is meaningless? It isn't the mesh that gives it physical meaning. It's a combination of two entities, materials, and properties that provide a given mesh body a physical definition. So what happens is, so really in this order, HyperMesh identifies a area or your 2D element and multiplies it by the thickness property to create a volume. It knows some area, and if it applies its thickness on top and bottom of that sheet, it turns a flat piece of paper into a box. That's the volume. And now that it knows how big that volume is, it's going to take the material definition, which is going to have things like your Young's modulus for your stiffness, your Poisson's ratio to describe how it can deform, and even the density to describe how heavy that material it is. And it will apply that volume, known as the element now, to this material to give it that stiffness value. So it first takes the element, applies the property to it. If it wasn't already a volume, it's been turned into a volume because of property. And then once it knows the volume size, it simply takes the material definition and applies it to that element. And now, with materials and properties assigned to elements, we have a physical clone or a physical representation of a part, not just a fancy drawing. That's really the idea there behind those materials and properties. And we're going to learn tomorrow how we can apply those once we're done getting familiar with some of the other meshing tools. So really, our next class is going to be very element driven, both in generating elements, reviewing them, knowing when to clean them up and how to clean them up. And also, now that we have these meshes generated, how do I actually make it a representation of my part? Because going back to what we said earlier, we want to make sure we have apples to apples representations. It doesn't do us any good to make all this time and take this HyperMesh training if we're not representing the same parts as we're going to design or manufacture with our different design teams there. So hopefully that kind of helped clear up where the stiffness was coming from with those 2D elements and why that's the case.
Thank you, Garrett. Yeah, and if it doesn't, we can, again, if they want a little bit more understanding, that ebook covers it also, so that might be of help too. There's currently no other unanswered questions, and we are past our deadline. And so again, appreciate Garrett, you're able to stay past. And again, our next session is tomorrow at the same time. So the same, everybody will be given a reminder email, but the same link should be what you can use again. But just look out for that email and pick on that. We look forward to continuing on here and seeing what Garrett has to do. And again, Garrett, a phenomenal job. Thank you so much, and look forward to again tomorrow. Thank you, everybody. Have a great day. Bye-bye.
No, thank you, everyone. Looking forward to seeing everyone in the afternoon tomorrow, and certainly any questions that we didn't get to today, feel free to bring those with you at the beginning of tomorrow's class. So thanks, Darius.